Welcome to Chapter 16, Lining Up Our Models. So let's get into what we're going to talk about today. We're going to explain data science modeling techniques. We're going to look at various models to interpret and understand the data on various levels. Lastly, we're going to look at another modeling package called IM, and that is going to help us in creating some linear regression models. So let's get to it. First, we need to understand what a model is. So the word model has a lot of uses in and out of statistics, okay? It could be a fashion model, scale model, replica, data model. Remember back in chapter 4, we said models help data scientists follow and understand the data? Well, in this chapter, we're using the word model to discuss prediction models, okay, created from a statistical analysis process. So even though we're using the same word model, it has a slightly different definition than what we've already used. Linear regression or linear modeling mean the same thing. It's a basic tool used by statisticians to interpret the data. So basically, linear modeling is used for prediction. Gauss was the biggest contributor, and he used it to predict planetary movement in the solar system and predict when planets would be hidden from view and when they would come back into view. In its most basic form, the idea is to put a straight line through a data set representing the connection between the independent variable and the dependent variable. This figure right here, it shows a linear regression over these 5 data points. This example uses the least squares method to find the best fitting line. The independent variable is the input, and that's the x-axis, and the dependent variable here is the output, or the y-axis. So now, traditionally what we say is y is a function of x. We don't say x causes y, two different things. This line fits pretty well, but notice it's still not exact. There's a few points that are not exactly on the line. Let's keep in mind that those discrepancies, that's actually important, but we'll talk about that later. Once this line is drawn, it can be represented by the traditional simple linear equation of y equals mx plus b. M is going to be your slope, b is your y-intercept, or the height of the line, okay, and x is your variable. Once you have that equation, you can predict values greater than 5 and things that are going to fall off this end, or even less than 1 and things that are going to fall off this one, if that's a possibility. Let's take a real-world example look of this modeling tool. This example is going to look into oil changing vehicles. Oil changes in vehicles. We have a fleet of vehicles for an organization, and it replaces its vehicles after every 3 years. What we want to do is create a data-driven, proactive approach to scheduling maintenance on these vehicles, okay, and the oil changes. So first we're going to define a data set, okay? We're going to have the number of oil changes, the cost of repairs, the number of miles in each vehicle. We're going to create a data frame with these 3 columns and named oil. Now, if I say view oil, let's take a look at it. It's going to in the tabular form. Sorry. This is our data set. Our first column is the number of oil changes in the past 3 years. The second column is the cost of repairs, total cost, and the third is the number of miles driven in each vehicle. So for our analysis, the independent variables are going to be the miles and the oil changes, okay? The dependent is going to be the repairs, because we want to see if oil changes and miles have any effect on the amount that we spend in repairs. With this, let's figure out if any of this is related. The independent variables, okay, are going to be the oil changes and miles again, and the dependent is going to be this repair, okay? The dependent is the one you are trying to predict. Okay, it's an easy way of kind of remembering what you're trying to predict. So we're trying to see if the number of oil changes, if we can predict how much we need to spend in repairs over a certain amount of time. Using the plot command, remember, we're going to do independent versus dependent. We can visually see this relationship. Now here, it's just oil changes versus repairs. Okay, now we did say we were going to have two. We're going to look at the second one here in a minute. It does look like there is a general trend here, right? When the number of oil changes is low, the repair costs are high, and vice versa. Okay, that's very interesting. So we can kind of see there is a pattern developing. Let's see if there's a pattern between miles and repairs. So we create the same plot, except this time, again, we're using miles versus repairs. This chart just looks like a scatter plot, okay? There doesn't really seem to be any kind of pattern here. So let's go back to that first one where we actually had a pattern. We're going to use a new R command called LM for linear modeling. Okay, it's used to find the linear regression and to fit the linear models. Okay, the LM command places its output in a data structure. So we stored this result of this data structure into a variable called model1. The format of the command LM is parentheses. Okay, and inside there we have formula equals. That is going to be the model specification. Okay, let's look at that a little bit closer. We've got repairs tilde oil changes. Okay, the tilde is going to tell which is the independent, which is the dependent variables, okay, to include in your model. So it's saying take the dependent variable of repairs and compare it to the independent variable of oil changes. Okay, so this takes the form of y tilde x, if you look at it, if you think about it in the graphical form. Okay, here we read it as use oil changes to predict the repairs. Okay, the last thing you send to it is the actual data frame. Let's look at a summary. So let's do a summary of a model X and let's see what happens. This is going to display information for us to determine if we're happy with this model or not. Okay, so the coefficient of determination, or the R-squared value, that's going to be the proportion of the variation that is accounted for in the dependent variable by the entire set of variables. Okay, from 0 to 1, or 0 to 100%. Okay, so here we've got the R-squared value way down here of 0.8653. Okay, you can look at that as saying 87%. So that means that oil changes account for about 87% of the variability in the repair cost. Okay? For significance testing, we look at this p-value, or the PR with the greater than absolute value of t, this thing over here, that are outputs. Okay, the numeric value that's given here, that is the probability of observing a result this extreme under the assumption that 0 is the true reality. Okay, lots of words. A result like that 87% would be very unlikely because it is so far away from the 0. Okay, a p-value of less than 0.05 can be read as statistically significant and not due to randomness. Okay, both the y-intercept and the slope coefficient, those are significant because that's what's going to give you your equation of that regression line, right? We said mx plus b, slope is m, b is the intercept. Okay, the residuals are the difference between the actual observed values and the values the model predicted. So looking at the distribution of these residuals across, data points, it's going to help determine if the model fits the data and for the median to be close to 0. Okay. Coefficients of the model are two unknown constants that represent the intercept and the slope terms in the linear model, the m and the b. The intercept is the expected value of repairs. Okay, the second row in the coefficients, that's the slope. That's the effect of the oil changes on the repairs. That's a lot of great information, but it is a lot of information. A lot of statistical information. Okay. What you can also do though is you can add AB line to your plot to plot the regression line. Okay. So according to this model, we should do as many oil changes as possible, right? Because the higher the number of oil changes, the cost of repairs. If I go over here to say 9.5 oil changes, it looks like I'm not going to have any cost for repairs. So according to this model, we should do as many as possible. Now, let's do the same thing, but let's add back in the miles, okay? If we look at the summary here, the difference is we say here oil changes plus miles. Okay, we're adding the miles back in, and we can do that with this linear modeling. If we do the same summary, we can look, and there's not much of the change on the data. Okay, we went from 87% to 88%, very, very slight, and actually it was an 87 roundup. This is what, an 89 roundup, or no, 88 roundup. Very, very, very slight. Okay, the one thing you do want to look at is this PR column that we talked about. Remember, we said the smaller the value, the better. So if I look here, my miles has got a 0.2. That's actually very large. Okay, this is going to back us up with the fact that the miles are not influencing the repair costs. Okay, so we are just as good sticking with our original model as if we had added the miles back in. This is a way to support your assumptions of removing different pieces of this puzzle. I could put this out there in a report and say, well, my miles, by this coefficient has no, very little influence, so it is going to be removed for simplicity. Okay, so you can see how all of these things are going to help you and give that confidence behind how good your model is. One item we did not look into in this model was the cost of the oil changes. So here we're going to add an additional cost of an oil change as $350. That is way too expensive if you ask me, but whatever. Let's create an additional column called oil cost change, and we're going to take the number of oil changes and multiply it by that $350. We're going to add another column as well called total cost, and we're going to take the oil change cost and add it to the repair cost. Okay, let's plot now the number of oil changes versus this new total cost and put a regression line. What do you think is going to happen? Okay, you got your idea? Now let's see. Whoa. According to this model, we shouldn't be doing any oil changes, okay? It's just not worth the cost. But remember, what cost did we use for these oil changes? We used $350 for an oil change. Again, I don't know where the book got $350. I'm assuming it has to do with downtime and blah, 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 okay? $350. But this model basically says that you have increased your total cost of maintenance by increasing your number of oil changes. Well, yeah, because your oil changes are actually outnumbering your repair costs if you look at the original table, okay? One oil change was more expensive than some of the total repair costs in this original model. Here, we can calculate the total cost for a given number of oil changes. You can see how the cost of this oil change is a huge contributor. We go from, $652 up to $3,500. Okay, so because that oil change is such a large contributor in the total costs, it's throwing your numbers off. Keep in mind that the R-squared value is artificially inflated here, and it should be ignored since the total cost is calculated as a function of the oil changes, okay? Your best practices is to keep the dependent and independent variables completely independent of each other. Okay, well, I know that sounds a little redundant, but here remember, this total cost is including a $350 amount times the number of oil changes, and you're plotting that against oil changes. You don't ever want to include an independent variable in a regression analysis if it has a formula connection? That word. If it connects by formula to the dependent variable. Okay? That's completely different than your y equals mx plus b. This is saying that your y is a function of x and has an x in it to calculate your y. Okay, completely different. Hopefully that makes sense. That's actually all for today's lecture. Nice and short and sweet. Okay, next time we're going to go over the next two chapters and we're going to look at association rule mining to discover patterns in lists of items. And then we're going to look at vectors again, and we're going to look at support vector machines, or SVMs. As always, I'm here for anything you need. I sincerely apologize for the CSV not being included in the assignment. I did move the assignment due date out a couple days. I'm going to take the late penalty off because that was completely and utterly my problem. I feel so bad about that, you guys. And then on top of that, I had no power like all of Saturday into Saturday night. So I couldn't even fix it for you. If there's anything you need, email me. I will get back to you as soon as possible. And as always, happy coding!